There. Easier for noting what's in each video. All right, so we last left off, we were doing the objects rolling down the ramp. And the conclusion was that objects which had mass closer to the center of the axis of rotation would move faster. And so let's bring out these things. These two objects weigh the exact same thing. The difference is where the mass is distributed. And you can sort of tell, I don't know if I can line it up perfectly, but you should be able to see through the ends over here, but in the middle, it's darkened. So hopefully you can see well enough that, I don't know how much I need to tilt it, but it should be, you should be able to see all the way through on the ends here, but not in the middle. This one, on the other hand, has the outside, the mass, most of the mass is on the outside, but the inside doesn't have anything there. So the big difference between these two things is just where the mass is distributed. On the red one, it's in the middle. On the blue one, it's on the outsides, primarily. So, which one can I whip back and forth easily?
The blue one?
Red.
So I got a vote for blue and a couple voting for red?
Supposed to be for red, because the red is right where your hand is at, and that's where the mass is at.
Yeah, yes, the mass is right at my hand here, and not at this one that's farther away.
Okay, yeah, I changed to red.
Yeah, so I can whip this one back and forth. This one's a lot harder to do. Man, I can feel that in my elbow. Last time I taught, or when I taught elementary school, they had a pole on the playground. And some of the kids would run up and they'd jump on it and they'd go swinging around as they're holding onto the pole. It looked like a lot of fun. And I thought, hey, I'm in my 40s, sure, I can do that too. And I made a new injury on my elbow when I did that. Occasionally it flares up. Oh, foolish adults. All right, so the more mass is in the middle, the easier it is to get it to roll. Now there's another thing that if you wish to know at the break or after class, I'll be glad to show it to you. It is beyond the scope of this class. But the mass of the object itself, if I'm dealing with a large solid ball and a small solid ball, so both solid, and I'm rolling them down an incline, they'll get to the bottom at the same time. That's why when I had the iron hoop and the aluminum hoop, they got down roughly at the same time. Because the radius and the actual mass are not critical when determining how long it takes to get to the bottom. It's the distribution of mass that's key. Taking notes on it? Okay. And I can work through the math and show that why at the point at which mass and the radius cancel out. I'm not going to subject that to you unless individually you would know it. So if I'm looking at a formula for a moment of inertia, so let's do a solid ball was 2/5 mr squared. Hollow ball two-thirds mr squared. And not asking you to have these particular formulas memorized. If you need to know them, you would look on the first page to see it'd be a capital I with a subscript of whatever the object is. Both rotating about its center. So for a solid ball, or hollow, whatever that one is, it'd be rotating about that middle there. Which one has more mass distributed closer to the center?
The hollow ball,
Why do you say that?
because I thought that's where the center of gravity was, in this middle.
The center of gravity is still in the middle of both of them.
Okay.
I think it's the solid ball, cause the hollow ball like doesn't have anything inside of it, so more of the mass is like around the outside.
Looking at the equations, how could you tell which one? You are correct, but looking at the equations, what's the key which tells you which one has more mass closer to the center?
The 5?
Oh, 5, yes, but something a little bit, looking for something more general. If I had another object, what can you tell me about this distribution of mass?
It's split evenly.
In comparison to these two. I hope this hasn't devolved into a read my mind exercise. All right, so we've established the more mass is closer to the center, the easier it is to get it to move. I raise these 3 objects. Which one comes in first, second, and third?
Would the unknown one come first and then solid and then hollow?
Why, what you thinking?
I'm trying to judge it based on how big each fraction is.
Ah. So which fraction is the biggest?
The unknown one?
2/3.
Yeah, 2/3 is bigger. 2/3 is 0.67-ish. 1/2, 0.5, and this is 0.4.
So
Oh. Sorry,
hollow, unknown, and then solid?
flip.
Oh,
First, second, third.
okay.
The bigger this number is, the more mass is distributed outside.
Okay.
Thus, for a hoop, MR squared, got a 1 in front. All the mass is at the same distance away at R. So the bigger the number is, the more the mass is distributed outward, and the slower it's going to be. If we look at it from an energy point of view, I have K of 1/2 mv squared, and then rotational kinetic energy of 1/2 I omega squared. I got my 2 kinetic energies here. So I got a ram, starts at rest, it has all this potential energy. As it's rolling, this is just like the ski problem, as it rolls, you've got force of gravity acting on it, its weight acting on it, and normal force. There's friction also, but friction's not doing any work, and I'll explain that in just a second. So as it rolls, we have normal force acting this way. Let's draw the diagram over here. We have normal force acting this way. We have weight acting down, and then there's some friction acting right there. Let's assume an ideal roll, static friction. Normal force is not doing any work because it's moving perpendicular to the movement as a net result. Weight is doing work. It's conservative work. This would conserve energy. So this is no work. Same reason as the ski problem. Friction is not doing any work because friction is acting at that point right there where contact is made. And if you looked at a spot on here, as this thing rolls down, what you would see is that a point would be doing this. friction is acting perpendicular to that movement of that tiny little bit that's touching. So the friction ideally is not doing any work if it's static. In reality, anything that rolls, there's gonna be a little bit of static, a little bit of kinetic. Thus, there's a term that some folks use called rolling friction, which is a combination of the two. What I'm getting towards is that energy should be relatively conserved as it rolls down. So I start out with all this potential energy, and it has to go into kinetic. Well, I got two kinds. Some of the energy goes into getting it to roll, the other part of the energy gets it to move down the ramp. This is the energy of going down the ramp, this is the energy of getting it to roll.
What you said?
Sorry?
What you said?
This is the energy dealing with it's moving down the ramp. This is the energy which deals with it's rolling.
Oh, okay.
Therefore, the more energy that gets it to roll means there's less energy left over to get it to move down the ramp. And I need more energy to get down the roll, the bigger that fraction is for our formula for I. That fraction is what affects it, from the math point of view. So if all the mass is right there at the center, then not much needs to go here. And there's more energy left over for getting that thing to move down the ramp. And therefore it'll be faster. People are stunned with the awesomeness of this. Excellent.
Cause isn't it rolling down the hill?
Pardon?
Isn't it rolling down the hill?
It is rolling. What's the issue there?
I don't know. I'm probably making it something that is not. It be
Yep.
like that sometimes.
From an energy point of view, I'm just saying that it rolls down the hill. This is the part with the down the hill part, and this is the rolling part.
But you said if we have less of rolling, we'll have, the speed will be faster?
Yes. That is what I was claiming.
Okay.
Other questions or comments? All right. Let's, still in chapter 8, let's change topics a little bit. Chapter 8 throws a bunch of little things in. What is that a symbol for?
Velocity.
What is that a symbol for?
Speed.
On a roll. What is velocity?
Direction and speed?
Okay, that's the one I wanted. Speed and direction of movement. Flashing back to a question that I asked early on. When you are driving, what are the 3 accelerators that you have access to? From a physics point of view.
Brake, gas pedal. Wheel, stick.
Make it an automatic transmission so you don't have to put up the stick. I heard somebody else say something?
Wheel.
The wheel, yes.
Why I always wanna say the windows? Every time. What did y'all say it was?
Wheel.
The
I
wheel.
know, okay.
Steering wheel. I assume steering wheel. Because brake and gas will affect this. The steering wheel will affect this. So we have dealt with the velocity changing because of change in speed. That's pretty much all the math that we did in chapter 3 was that type of thing. Have I done the spinning something over my head and throwing it?
Hmm?
Okay, so let's talk about that.
What was it you said?
Spinning something around my head and then releasing. I said and throwing it. I haven't done this yet, right? Okay. Let's see if I can do this without hurting myself.
Traumatic flashbacks.
All right, so what I want to do, because we're about to talk about the velocity deal because of change in direction. What I want to do is I want to hit that spot right there. And I'm going to be standing over here. I should check the string to make sure it's not about to snap or anything. All right, so I'm going to swing this around. And the question is, where do I release it so that I can hit that spot? So let's draw up an absolutely incredible model of our classroom. The door right there, there's a door right here. I'm gonna hit that spot right there, and I'm gonna be standing basically here, twirling this thing around in that direction. From an overhead point of view, I guess that's counterclockwise. Where do I release it so that I hit that mark? Now, in terms of you're communicating to me, let's sort of treat it like a clock. So if you say 12 o'clock, I'm releasing it here, 9 o'clock, 6 o'clock, 3 o'clock, and so forth. If somebody says 1:30 and someone else says 1:31, I cannot differentiate between those two.
Yes, you could.
I can pretend, but I appreciate the faith. All right, so someone just toss out,
3 o'clock.
what'd you say?
3 o'clock.
3 o'clock, so,
Nah, cause then it'll go.
all right, so you're changing your mind on that? I wish I could hear you better, because every time I point to you, because I think you say something, you just quiet down.
You think if I let it go at 3 o'clock, you go that way or that way?
Well, that's part of what do you think?
I'm gonna say, let's say 3 o'clock.
You're going back to 3 o'clock? Okay. You're gonna live with that. Okay. Any other speculation besides 3 o'clock?
I'm
pretty,
thinking,
yeah.
oh, go ahead, Chancey.
3 o'clock is right, I think, unless my mind's gonna be completely blown.
So I got a couple, three, we'll say 3. Rebecca, were you going to something different?
I'm gonna guess 6.
6?
Just so I have a guess.
3. Another vote for 3? Something besides 3 or 6?
2 o'clock.
12. 12 o'clock is good, no. 12 o'clock might have been good, but. I'm just thinking about.
I just want to say, I've done this many times. I've never hit a student doing this.
So you plan on hitting us?
No.
Oh.
I'm gonna, at some point, I'm gonna ask some of you to move, and just so you know. And for the record, I did not hit Scott, and this is for the video too. I did not hit Scott. I was,
He said he is God.
I got closer to Scott than I intended, but I did not actually hit him. My first period, this teacher in middle school, first period I was doing this, and I was aiming for one particular spot. I released it just slightly late. It came within a couple of feet of Scott. It did not actually hit him. Last period comes around, somebody comes in and says, Dr. Fox, I heard you hit Scott this morning. I did not hit Scott. All right. So any other speculation besides we got, I guess, 12, 2, 3, 6. All right. So let's do this. I'm going to ask, I guess let's just start out at 6. So I'm going to ask you 4 to sort of move back. Well, Latoya was wondering which way it would go. So 6 o'clock is going to go, oh, I guess I'm doing 6, I said? So that means that I guess potentially it could go that way, but let's just go with faith at this point. that physics will hold. Now,
So probably in physics, huh?
there are days.
What happens if you hit one of those?
Then I can no longer legitimately make the claim that it is a student. It's a rubber stopper at least. All right, hoping not to hit the camera. All right, so I'm gonna release it when it gets here. I have to go slowly enough so I have some control, which is one of the mistakes I made that cable day. All right, so 1, 2, 3.
Okay.
So that was at 6?
That was the 6. All right, so let's do 3. So 3 o'clock would be roughly here. I don't think I'm gonna, thank you. That makes it a little bit easier. All right, so 1, 2, 3. Hopefully you're getting a general idea of the way it's gonna go. I'll do noon this close. Depends on how much faith you have in my coordination.
Don't hit my glasses.
I feel like you just challenged me. 1, 2, 3. All right. So it should be somewhere around in this area right here. Depends on, at that point, you start getting into how well does my drawing match where I was standing. But when released, this one went that way, that one went that way, this one went roughly that way, this one. Given this drawing, it should be somewhere around 2 o'clock, but given reality. So, Newton's first law of motion. Objects want to keep doing whatever they're doing. So because when I release it, it went this way, that is telling me that the velocity at this point right here was that way. Velocity at this point was this way. Velocity at that point was that way. The direction of the velocity is what's called tangent to the path. So, got something dropping around in a circle like this at this point right here. That is the direction of the velocity. At this point right here, that's the direction of the velocity.